Hey everybody, welcome to this video on radiometric resolution and contrast stretch. You know, I was trying to think of a joke to start this video with, but the times are just so dark, I'm not even sure I can come up with anything. Plus I've been up since 4, so we'll just jump right into it. In this video, I'm going to tell you about what is radiometric saturation, what is a radiometric response curve, and what is contrast stretch. Essentially, we're going to talk about how images are collected and how the photons that are collected by an image actually get translated into a file and then displayed on your computer screen. So I'll actually motivate the video with a science problem really quickly. A big problem in our area is water quality. There's a lot of farming, and sometimes cow manure or fertilizer runs off from those farm fields into the river and goes into the lake as pollution. And it's a huge problem. And as people try to manage this, one idea is actually to monitor farm fields and their status using remote sensing. So you could imagine you might want to be able to distinguish between farm fields that are covered by grass or crops and farm fields that might be freshly plowed and more vulnerable to runoff during a big storm event. So we'll run with that idea. And here's a Landsat image taken in October 2005 of the Vergennes area. This is Vergennes, Vermont right here. This is Otter Creek right here. And this is Lake Champlain over here. So imagine you're looking at all the farm fields in this picture, and you see that some are green, those are hay fields. Some are brown, they might be freshly plowed. But what about these white ones? Some of these white fields, it's really hard to tell what's going on with them. Why are they so bright? Why are they white? The reason is because the detector is essentially saturated. There was so much light coming off of those fields that it overwhelmed the detector, and the detector wasn't able to divide that light into meaningful intervals that it could then display as different shades. It just took all that bright light and assigned it all to one shade. So that's a way to describe saturation or radiometric saturation, when the light is so bright it's overwhelmed the detector. So it's worth understanding how detectors work then a little bit. A satellite camera is just like any other camera or modern camera. Images are collected as photons strike a CCD chip, right? So this CCD chip here is literally divided into a grid of photosites, and photons come in and they hit those photosites, and the brightness of any given pixel in the resulting image depends on how much power was actually delivered by photons to that pixel, which corresponds to some point on the ground. And here's the equation for power. You're going to need this in an assignment if you're in my class. It's just photons per second, so the rate of photons striking the detector, times the number of joules per photon, or the energy per photon. And keep in mind, this changes by wavelength, of course. Okay, so the detector has done its job, right? It measured all these photons. It figured out how many watts hit each site on the detector. How does it actually convert that to a digital number that can then be stored in a file? This is a really important concept, and it's called the radiometric response function. And this is the mathematical equation that actually converts the measured brightness or radiance into a digital number and then stores that digital number into the image file, right? Each pixel gets a digital number that corresponds to the measured radiance in that picture. And so here's how that works. So this is digital number down here. It's 0 to 255 because this is 8-bit data. So remember that we have 256 possible digital numbers we can use to store information. And then on the y-axis is the measured radiance or the brightness. which is a continuous variable based on how many photons hit the detector. So what the detector does, it measures the radiance, okay, here, and then it assigns it to a digital number. And this line governs those assignments. And in particular, L min is the minimum radiance that a detector can actually assign or will assign to a digital number. Okay, so anything below L min, all of those radiance values are going to get assigned to 0. Likewise, anything above L max, all those radiance values are going to get assigned to 255. So if it's above or below the min and max, it'll get assigned to the minimum or maximum digital number. And then the slope of this line is called the gain. And essentially, this is what determines what we would call the radiometric resolution. This is a really important term, radiometric resolution. This is the radiance per digital number interval, okay? In other words, it's the slope of the line. How many watts are binned into each of the 255 digital numbers, okay? And so you could imagine that if this is a very steep line, okay, this is a steep line, then you have a lot of watts into each digital number, which means when you go to display those, you can't tell between small differences in radiance. If this is a shallow line, then you have very few watts assigned to each digital number, and it's quite easy to display small differences in radiance. Okay, so a steep line is a low radiometric resolution. A shallow line would actually be a high radiometric resolution. So getting back to these fields, what we can say is the reason these fields appear white is because either they were so bright, the radiance was above L max, right? So they're saturated. Or perhaps digital numbers were recorded. Perhaps the radiance wasn't above L max and digital numbers were actually assigned. But perhaps the radiometric resolution is so low that we don't have shades of color available to distinguish anything on those fields. So I want to use that as a launch point. It's very common in image processing to actually use what's called a contrast stretch to try to take whatever radiometric resolution you have and try to improve that so you get a better display resolution. So in other words, is there a way we can try to see if we can tease out some different shades on these farm fields? So first, I need to tell you what is a display resolution. So the same way that your file may have 0 to 255 digital numbers, your computer monitor may have 0 to 255 display levels. And in fact, I think most modern monitors have more than 255 display levels. I'm not sure how many, but the point is that you have all of these digital numbers in your file, right? Okay. And they may not be spread across the entire range from 0 to 255. It may be that in your image there was nothing especially bright, so no pixels showed up over here. Maybe there was nothing dark, so no pixels showed up over here. Everything's clumped right in this range, okay? Now, if you go ahead to display this and you just assign each digital number directly to its corresponding display level, like a 1-to-1 assignment, you may not be able to tell those pixels apart because they all may appear as a fairly similar tone or shade of brightness, right? Because you're only using a small range of the display levels or the different brightnesses that are available to you. So a contrast stretch, so getting ahead of myself. So here's what it looks like. If we were to take our Landsat image of of Vergennes area and just do a one-to-one digital number to display level, here's what it looks like. Here's our histogram of digital numbers, okay? And here's what it looks like if you display it that way. You can't see anything because you're only using a small range of those grayscale shades. So now we bring in the idea of a contrast stretch. What a contrast stretch does is it actually maps those digital numbers across the full range of display levels. So if you imagine here was your digital numbers grouped together, we're now going to expand those out and assign the higher digital numbers, now assign them all the way to the maximum display level. Take the lowest digital number and assign it all the way to the lowest display level, which spreads the values out, and it uses all of those display levels to magnify those differences. And so here's what it looks like when we have applied a linear contrast stretch. Okay, suddenly we can see the difference between gray, black, white, and we can see all this detail. Our eye can resolve all this detail that it couldn't before. The detail was always there in the file. It's just that it wasn't being displayed in a way that our eye could tell the difference. The contrast was too low. Oh, and here's what that contrast stretch looks like. So we stretched this histogram, and then the purple shows how it was stretched, shows the display levels. Purple is display levels, gray is original digital numbers. Okay, so you just learned about a linear contrast stretch. Turns out there's a number of different types of contrast stretches, which can be effective depending on the distribution of digital numbers in your image. So really common ones are the percent or the max-min clip. Essentially what this does is it clips outliers off of your digital number range and then applies a linear stretch to whatever's left. And you can specify what those outliers should be using either a percent, like clip the top 2% and bottom 2%, or using a max-min. You can say clip off any value above 150 and any value below 100, and then stretch the rest. Okay, so that's percent or max-min clip. Equalization. An equalization stretch will redistribute the digital numbers so that the same number of digital numbers are assigned into each display level. So that's a nice way to make sure that you don't have any bunching or compression in any part of your data. All those digital numbers are as spread out as they can possibly be. But sometimes that doesn't work well, because sometimes you actually don't mind if some of your digital numbers are all displayed as the same tone. Standard deviation is another great one. Well, essentially what happens is you compute the standard deviation of the digital numbers, probably the mean and the standard deviation. So maybe here's the mean, maybe the standard deviation grabs 66% on either side of that, and then you clip the data at plus or minus the specified number of standard deviations. So you might clip it at plus or minus 1 standard deviation, plus or minus 2 standard deviations, or plus or minus 3 standard deviations, and then it would apply a linear stretch to whatever's remaining. And then finally we have a logarithmic stretch, which will redistribute the digital numbers based on a log transformation, and those tend to disperse the lower or darker digital numbers a bit more. Okay, so in summary, you've learned that power is the total watts that are hitting the detector. I didn't actually say this, but radiance is the watts per steradian per meter squared. So radiance is really a normalized version of power. A radiometric calibration curve is what a detector uses to assign the measured radiance values to a digital number. And then those digital numbers are then encoded as pixel values in the raster file that you are going to use. We learned that Lmin and Lmax are the lowest and highest radiance values that can be recorded. Radiometric resolution is the number of watts per digital number interval. Display resolution is the number of shades available on the screen, right? And what a contrast stretch does, it reassigns digital numbers to display levels so that similar digital numbers can be more easily distinguished as different colors or different shades by your eye. I know that was a lot, everybody. I hope you learned something.